range for sounds in general that we can hear are from 20 Hz to 20,000 Hz. So ultrasound is any sound that has a frequency above 20,000 Hz. So the question, what frequencies are above the range of human hearing, or any waves above 20,000 which we cannot hear, and that's referred to as ultrasound. Now, what we need to do is have a few uses of ultrasound, the same for infrasound as well in the future, but it's always good to have at least 3 uses in an exam to be able to state 3 uses of ultrasound straight away. So the main ones that we know of are pregnancy scans or fetal scanning. So for example, if a woman is pregnant, we can use ultrasound to create an image, as you can see. So fetal scans or pregnancy scans. We can also use ultrasound for sonar, which is also known as echolocation, for example. And basically we use sonar and ultrasound to determine the depth of lakes and oceans and the seabed of the sea. We can determine the shape and how far away it is using sonar and that echolocation using ultrasound. And then we can actually discuss the different animals that use ultrasound as well for communication, such as dolphins or bats. And when you're using that as an example, animal communication, you must be specific in the animals that you use. So for example, you would say dolphins or bats, communication or echolocation, but you shouldn't be saying animal communication because it's too general, it's too vague, and we don't know which animals then are actually using ultrasound. So dolphins and bats, communication or echolocation for ultrasound. Now, just to explain this fetal scan in a little bit more detail, because there are questions, especially in the worksheet, where you need a little bit more of an understanding of what's going on in ultrasound. You can clearly see an outline of a fetus inside a woman's womb, and you have those areas of white, so there's really bright areas that kind of give you that outline shape of the fetus inside. Now, the reason that we have that, and then the parts on the outside which are black, the only reason we can see that image of the fetus is because ultrasound has obviously travelled through the skin, the womb, through the tissue, the fat, muscle, and what's happened, it's been transmitted through all of those boundaries, reflected by the fetus, and then travelled back through those boundaries again, and then back into the ultrasound scanner, so we can create an image. Now, the areas of black around the outside, they're areas where those ultrasound waves have not been reflected and either were transmitted further, so didn't come back, or they were absorbed, and therefore we get that black outline with the really bright colours on the inside. So it's all about ultrasound being transmitted to the fetus, reflected by the fetus, and transmitted back. Now, you have to be very careful when you're doing ultrasound scans, because what you don't want to happen is when you send the ultrasound into the skin, if it travels from air to skin, 99% of the ultrasound is actually reflected at the skin boundary, so only 1% is transmitted, and then you're going to lose all your energy before it gets reflected back. So what we do, we know that ultrasound travels from liquid into the skin, and 99% is transmitted if it goes from liquid to skin. Now that's what we need, so what we do when we're doing ultrasound scans is we put a liquid gel onto the stomach, and we use the scanner with the liquid so that the ultrasound travels from liquid to solid, and 99% is transmitted, and only around 1% is reflected. So it transmits and then it reflects at the fetus. It's not reflected at the skin, which is not what we want. So we need to be very careful about how we use these scans and what we do. Now, in order to actually explain how ultrasound is used for echolocation, more specifically, we need to actually look at what's going on when a dolphin, for example, sends out a pulse of ultrasound, and then what the maths is taking place to actually determine a distance to an object using ultrasound. So the dolphin emits the ultrasound, which goes off into the ocean. They can't necessarily see the fish, so they're trying to figure out where is the fish using reflection. So the sound travels to the fish, it then reflects back off the fish, and the reflected ultrasound pulse is received by the dolphin. Now, obviously the dolphin has adapted and evolved to be able to determine a distance based on this information, but we're going to look at how humans can use it with an actual equation of math to determine an exact distance. But all we need to be able to understand is ultrasound pulses are sent out into the ocean, for example, into water. They're reflected by an object which is quite nearby, but a certain distance away. It's reflected by the object, and then the received pulse, or as we refer to it, the echo, reflection of sound. The echo is received a certain time later, and then we can use speed equals distance divided by time to rearrange and find distance to the object. Now, what we're going to do, very specifically, is, I'm just going to go through the uses one more time. We have fetal scans. There are also medical uses of ultrasound, such as destroying kidney stones. We have echolocation for bats, dolphin communication or echolocation, measuring the depth of the sea, or even detecting fish in the sea. So all of those are uses of ultrasound. Now, looking mathematically at this situation where we're using ultrasound waves, a ship is trawling the sea to find any old parts of sunken ships. The sailors on board want to find out how far the seabed is. So from the top of the sea in the ship, how far is it just to the seabed? We're going to use ultrasound to find that out. They send an ultrasound pulse at a speed of 1,350 meters per second and receive the pulse 25 ms later. Now, straight away we have something that we need to think about. 25 ms, which is a time, refers to 25 milliseconds. And we know that milliseconds can be converted back to seconds using times 10 to the power of minus 3. So that would be time equals 25 times 10 to the minus 3 seconds. Speed is equal to 1,350. We've been asked to calculate the depth of this sea. Now, the equation is speed equals distance divided by time. Rearrange that, distance equals speed times time. If we do that with the speed and the time, we find a distance of around 3.6 meters. But we have to be very careful now because we found what distance? The distance from the ultrasound pulse being sent to the seabed, reflected and coming back. The total distance there and back. But I've been asked for just the depth. So what I need to do is when I find my total distance, 3.6 meters there and back, I half that and I just find the distance there, which is 1.8 meters. So be very careful in the exam. What have they asked for and what have they given you? Use the speed equals distance over time equation. Rearrange for distance if they ask for distance, which is speed times time. If they ask for time, for example, then it would be time equals distance divided by speed. So make sure you rearrange it correctly. And then ask yourself, have I found the total distance there and back? Do I need that total distance, or do I need to halve it to find just the depth? Or in some cases, do I need to double something because I was only given there, but I want there and back? So it's the same using speed equals distance over time, but sometimes you have to halve the value, sometimes you even have to double the value, so be very careful. And then one more example of a common question when we're talking about ultrasound in an exam is using an oscilloscope, which is a device that turns vibrations and sound waves, for example, or signals and waves into electrical waves. So on the screen it produces these electrical signals so you can see them because we can't see the sound. And what's happening here is you have a transmitted pulse of ultrasound. So you send the pulse out, that's the first spike. Then a short time later, we're sending the ultrasound into a layer of muscle. The ultrasound goes into the muscle, this is this spike here. It reflects at the other side of the muscle, at the boundary, it comes back, and we receive the echo or the received pulse a short time later when it travels through the muscle and back. And as you can see, this is the second spike here. Now, we're not going to worry about the difference in height of the spikes at this point, but how can we use this to determine the thickness of the muscle? So the speed of these ultrasounds is 1,585 meters per second. That's the speed, that's fine. It says on here that each division, each horizontal division represents 2 microseconds. Now what that means is every horizontal square on this oscilloscope grid is 2 microseconds. So immediately I'll turn the 2 microseconds into seconds. 2 times 10 to the power of minus 6 is micro. But then I also need to know how much time has passed from the first spike of the transmitted pulse until I receive the echo. So how many squares on the grid? 1, 2, 3, 4 squares on the graph, which each represents 2 microseconds. So 2, 4, 6, 8 microseconds for the ultrasound to go through the muscle and all the way back. So 8 microseconds is there and back. So if we just want the thickness, we're going to find the distance again using distance equals speed times time. We're going to do 1,585 multiplied by the 8 microseconds, which is 8 times 10 to the power of minus 6, That's the total distance through the muscle and back. So if I just want the thickness of the muscle, I halve that distance and it tells me the thickness of the muscle. So that's how we use it. It's exactly the same as the one before, except we're using a graph to find your time taken to travel there and back, using the gap, the distance between the two spikes, and we know that each square on the grid is 2 microseconds, which we convert. Now finally, the very last thing when we're looking at ultrasound and questions, we mentioned that the spike of the transmitted pulse is higher, the amplitude is greater than the received pulse, which is this spike here, which is actually smaller. Now, question in the exam might be explained why the received pulse has a smaller amplitude or is lower than the transmitted pulse. And the amplitude of a wave just refers to the amount of energy that the wave is traveling. So if it has a lower amplitude, it's a lower spike, it means it has less energy. So the energy of the received pulse is going to be less. That means that some of the energy from the transmitted pulse was wasted when it traveled through the muscle and back. So energy has been wasted, generally due to dissipation into the surroundings by heating. In some cases as well, it could be that some was transmitted, but some was reflected, and also obviously sometimes when it reflects off an object, some of it may reflect in different directions, so it can be scattered, and you don't actually receive the same wave as you sent when it comes back. So energy has been lost, so there's less energy, and the reason for that is multiple: dissipated to the surroundings by heating, scattered in different directions, transmitted instead of reflected, and those are your different possibilities in different contexts, okay? So they're the general and most common questions when we're talking